Hi there, and welcome to lecture 3 of Fox. We're going to be talking about making precise statements and, why. Just a quick recap of where we were. Last time we introduced the discrete objects, the fundamental objects that we're going to be talking about in this course, sets, sequences, and graphs. Again, then we introduced you to the notion of proof, where we emphasize the difference between an inductive proof, one based on data, which always leaves room for doubt. Maybe you didn't consider all the possible data, and then a deductive proof, which leaves no room for doubt. Ironclad, take it to the bank kind of proof. We discussed several examples of proofs. The dating game. We showed that nobody can meet more than 12 people. We discussed even squares. Okay, and a square is even only when it came from an even number, and even numbers are even squares. We talked about extremist parties, where you can guarantee, groups of mutual friends who can have a good time, or groups of mutual enemies who can have a war. Okay, and then lastly, we introduced the well-ordering principle, this fundamental axiom that is very important for discrete math. Ultimately, it will lead us to something called the principle of induction. In the last lecture, we used the well-ordering principle to show that the square root of 2 cannot be represented exactly as a rational number. There's no ratio of numbers that exactly equals the square root of 2. That's interesting, because it means that there are these other numbers, and we need to develop a theory for these other numbers. Okay, and those numbers turn out to be the reals. We won't say much about that, but proofs are very important in convincing us of statements. And once we have statements that are proved, you can take it to the bank, you can bet all your money on it, it'll never be false. Okay, not like an inductive proof. Okay, today's lecture, making precise statements. And we're going to talk about fundamental precise statements that you might like to make, and how you can combine, basic statements into more complicated statements called compound propositions. And lastly, we're going to introduce this concept of quantifiers, the ability to make statements about many things. Okay, so let's start with statements. Okay, 2 plus 2 equals 4. Well, that's a true statement. Nobody will say it's an ambiguous statement, and everyone agrees that it's true. 2 plus 2 equals 5. Okay, this is a false statement. Okay, but now let's distinguish a false statement from an ambiguous statement. So there's no ambiguity here. 2 plus 2 equals 5. We all understand what it's saying. It's just that it's false. Okay, you may have cake or ice cream. Now, there's an ambiguity here, which is, can you have both? So when Malik was going to birthday parties, the parent said, you can have cake or ice cream. Malik is greedy, he says, can I have both? What the parent actually means is, you can have cake or you can have ice cream, but you cannot have both. So actually, the parent means to say X or. And, a computer science parent at a party would say, you can have cake, X, or ice cream. Okay, but we need to pin down what we mean by or, so that there's no ambiguity here. The version of or that we will use in this class is that you can have cake or ice cream or both. Okay. If pigs can fly, then you get an A. Okay, now that's a fairly complicated sentence. There is no ambiguity here. Nevertheless, okay, to the uninitiated in propositional logic, which is basically the subject that we're talking about today, you might wonder, since pigs cannot fly, is it possible for me to get an A? Okay, and that's resulting from a common confusion regarding these kinds of if-then, what are called implication compound clauses, okay, compound propositions. Okay, now let's get back to this joke that we said, there is one soulmate for every person. Okay, now why is that a joke? It's a joke because there are two ways to interpret this sentence. Okay, the first is that there is a single soulmate who is the soulmate for everyone. So there's this busy soulmate, and everyone shares this soulmate. A second interpretation is that every person has their own special soulmate. Okay. Now, which did the girl mean? The girl meant 5B. And what did the boy interpret? The boy interpreted 5A. Okay. So, why do we care? Okay. Why do we care that this sentence can be interpreted in two different ways? And the reason we care is that we are interested in proof. And if you're going to prove something, you had better know exactly what it means. So let's think about what it would take to prove 5B. Okay? So we're going to ask, imagine the world is composed of only 6 people, A, B, C, D, E, F, our usual friends. Okay? And we're going to ask them who their soulmates are. So A says, Sue is my soulmate. B says, Joe. C says, Sue. So Sue is popular. Okay? D says that his soulmate is a red Porsche. Okay? So D is a peculiar guy. Okay? E says Sue. So Sue is really popular. And F says Sam. So what we observe from this is that every person does indeed have a soulmate. Okay? And so, 5b is essentially proved. Every person does indeed have their own special soulmate. But we have not proved 5a because it's not clear that one single soulmate is a soulmate for everyone, which is what we need to prove 5a. So you see that 5a is much harder to prove than 5b. Okay? And have we disproved 5a? We haven't even disproved 5a because it's possible that, for example, A also has Joe as a soulmate, and C also has Joe as a soulmate, and so does D, and so does E, and so does F. They might all have Joe as a soulmate. It's just that when you ask them, they gave you their maybe preferred soulmate. Okay? So we haven't disproved 5a either. So an interesting question is, how would you prove 5a? Okay, a proof might go like this. Well, after we made our first round of questions, we might have said, well, B, is Sue your soulmate? B says yes. Okay, C says yes. Okay, D says no. Okay, now we are stuck again. So Sue is clearly not a soulmate to everyone. So we go back to A. Do you have another soulmate? A says Joe. Okay, now B also has Joe. We might ask C, is Joe a soulmate? C says yes. Okay, we might ask D. D says yes. E says yes. F says yes. Okay, if all of them agree, then we found Joe as a single soulmate for everyone, and we've proved 5a, but not everyone might agree. Then we go back to A and ask for another soulmate, and this process goes on. It's very hard to prove 5a. And in mathematics, statements like 5a are equally hard to prove. Statements like 5b are equally easy to prove. Okay? And so it's very important to know what the meaning of a statement is precisely before we try to prove it. Okay, so let's get back to our propositions, and we usually use the letters P, Q, R, S, these little lowercase letters to represent propositions. It's a shorthand. So rather than always writing Porky the pig can fly, we might label it P. Okay, and it's pretty clear that the statement or the proposition Porky the pig can fly is false, so we say that P is false. Okay, we'll label the statement you got an A, so that's a well-defined statement, you got an A. It's either true or false. Okay, we'll label it Q, and we'd like to know, is it true or false? We don't know. Okay, Kilam is an American. That's another statement. Okay, we'll label it R. 4 squared is even. That's another statement. We'll label it S. R, which is Kilam is an American, could be true or false depending on who is Kilam. Okay, S, the statement 4 squared is even, that is true. Okay, because 4 squared is 16, which is even. Okay. So here are some basic statements, P, Q, R, and S. And what we're going to do, okay, so basic statements are easy. You look at it and you can analyze whether it's true or false. And this is a property of any basic statement. Any basic statement has to be true or false. Okay. Now, what we're going to do is we're going to study more complex statements. Okay. So we're going to combine these basic statements by using what are called logical connectors, and in combining these basic statements or basic propositions, we get what are called compound propositions or more complex statements. Okay, so let's start with our basic statements. P, Q, R, and S. Okay, and the first non-trivial thing we can do a statement is take what's called the negation or the not. Okay, so not. Okay, and in this case we're taking not of P. So this wedge-like symbol is the negation, not P. And okay, how do we read not P? So not the case that Porky the pig can fly. And that's exactly what we say. It's not the case that Porky the pig can fly. Okay. Okay. Next example of a connector, and. So, we have the symbol, this upside down wedge. So P and Q. Okay, so P and Q. So in this case, P is Porky the pig can fly, Q is you got an A, P and Q is the statement Porky the pig can fly, and you got an A. Okay. Let's talk about the OR connector. Okay. So OR, P or Q. So this wedge is the symbol for OR. And in this example, P or Q, Porky the pig can fly, or you got an A. Okay. So these are the fairly standard Boolean connectors that we are used to in Boolean logic. Okay, now comes the most sophisticated of the connectors, which is called the if-then. Okay, so the if-then connector, and we write, so what we would like to say is if P then Q, and we write P arrow Q. Okay, so that stands for if P then Q. We could sometimes read it as P implies Q. Okay. So if Porky the pig can fly, then you got an A. All I did there is substituted what are P and Q. So if Porky the pig can fly, then you got an A. So these are the four main connectors that we're gonna be using. Okay. These are examples of those four main connectors in action. Okay. And what we need to do now is we need to pin down exactly what those mean. Not and then or are going to be easy because you're familiar with them, and we're going to spend a lot of time on if then. Okay. Because we need to know exactly what if then means. We need to know what these connectors do to statements in getting compound statements. We need to know how the truth values of individual statements gets translated into the truth values of compound statements, because we want to prove things, and we'll want to understand if then very carefully, because most of the things that we will prove in this course involve if thens.